this. I will put it online after I'm done in case you want to review it. So that's for you. I am going to share my screen. Just a second. And just to confirm, do all of you see my screen? Yeah?
Yep.
Okay, great. Let's roll through it. Remember, you're taking notes on things that you don't yet know, any terms that are unfamiliar to you, and any questions that you might have. Okay. If it is unfamiliar to you and you think, oh, I got it, I would probably write it down, to be honest with you at this point. Okay, we're starting. All right, so I'm gonna not look at myself. All right. Okay. So so if you know anything about the history of color theory, and you probably are covering this potentially in your other classes, but maybe not this early, Isaac Newton is actually the one that gave us the first theory in how we actually can construct our understanding of color. He didn't necessarily invent color theory, but what he did was he did these little experiments in his laboratory. I said laboratory, I know. Where he used a prism, and a prism is just essentially kind of like a pyramid, but it's a pyramid that doesn't have the three sides. It actually has more than that. And using that pyramid, he was able to distill the pure white light that was coming in through the window, and then separate that white light into the spectral order, which is actually what white light is, right? And we talked a little bit about this when we talked about photographing your work. And what he was able to do was give us basically that understanding pretty quickly. Initially, we as artists devised a way to understand that order by using the color wheel invented by Johannes Ten. And Johannes Ten gave us the 12 color wheel that gave us a concept of complements. And complements are very simple, right? It's the opposing color on the color wheel directly opposite. And we do a number of things with the logic of that complement. And we'll talk about that at length as the slideshow goes on. Munsell evolved his color wheel into a lot more colors. This is an oversimplification of that. But he was able to sort of give us a greater, further extended understanding of the prism of light, the spectral order, and how to actually classify these colors beyond just the 12 color wheel. In digital art, we will oftentimes rely on the Pantone codes, and all of you have heard of the Pantone codes. In fact, there's a song that I listen to in R&B that it's called Pantone. And what those are is a standardized format to code colors so that there is consistency across the board in print, right? So Becky from New Haven, Connecticut, can go and pick a Pantone color from her swatches or from a website on Pantone, pick it because she likes it, and go to her paint store and have them mix it up for her as close as they can based on their settings to put them on her wall. And that sort of standardization allows for a lot of flexibility. And it's a fairly simple code. The CMY code, though, is a little bit different, and that CMY code is a standard that is seen through screen, right? And in print. So, and we already went over that. So cyan, magenta, yellow, and black. And it's not the code that we use entirely for everything that we create digital images on, but it is the code that's used in order to calibrate your screen so that all screens look the same, right? Because all screens don't necessarily look the same. So we can use CMYK codes in order to calibrate a print from the screen. So it's used exclusively in printmaking for the most part. RGB is used just for screen though. So anything social media, websites, TVs even, are all using an RGB, the Roy G. Biv, right? Red, green, and blue, which, funny enough, if you use in conjunction with each other, you shine a red, green, and blue light all on the same spot in your digital world, what you're supposed to get is white light, right? Hex codes, though, are used specifically primarily in the Adobe suite. So hex codes are those little codes that when you go to your little dropper tool and you touch on the palette on your Photoshop, it's basically an alternative that is used primarily in the Adobe products in order to classify a color for screen. Okay.
Is
Yeah.
pure, what is the code for pure white? I ran into that while I was doing the.
It's 00000, I think. That might be black. It might be the
That's
code.
black.
Yeah, I
Okay.
can't remember what white is.
I
Go
okay.
ahead. Yeah, I don't know off the top of my head.
I can look it up.
I think white is like 255, 255, 255. Like if we're talking about RGB,
Mhm.
like just like I
Okay.
Yeah.
don't know. Don't take my word for it, but I think it's that.
Yeah,
Okay.
probably. And the beautiful thing about the hex code is once you memorize them, you know, especially if you're using the same color palette, you just type it in instead of trying to find it on your dropper tool, right?
Also, I have a
Mhm.
question.
Mhm.
Would we be using hex code, or are we gonna be like restricted with RGB and CMYK?
Believe it or not, you're already using hex code in Photoshop. So not only are you using RGB, you're also using hex code.
Right.
So RGB is what you're using for your screen calibration, and the hex code is what you're using in the Adobe product. And those are calibrated to speak to each other. Does that make sense?
hmm
And it's called the hex code because it makes a hexagonal color wheel, which is what you're looking at in the upper left-hand corner there, right? And it's just a way that they've classified it, right? Any product on the market is going to try to develop their own thing in order to, you know, copyright it and make it more difficult to use, right? So anytime anybody uses a hex code, they've got to refer to Adobe. So they make a dollar. But you are using both. When you go file print, you're using CMYK. Pantone, though, like for instance, when I've done public murals, what I've done is I've simply gone to the Pantone website and I've matched my RGB mockup that I made in Photoshop, and I've used their dropper tool in order to create the Pantone color for that, so that when I go to Golden Paints or when I go to the outdoor paint shop, you know, exterior, you know, glossy, they can mix that color for me as close as I can get it. It's not going to be perfect though. Pantone and actual color in physical form generally is not perfect to the colors that you're creating on your screen, because screen uses light and paint uses pigment. We'll talk about that in a second. So here we have what the spectrum of light looks like. When there is no light, there is only black, right? And this is called the additive process of color theory. And the additive process means that if you were standing in a theater and you had a red, green, and blue gel over a white light shining into a spotlight, all in the same place, wherever they're shining together, all three at once, you're creating white light. Okay? Additive process of light. And we'll get to the subtractive process in a second. Now, when we arrange these colors and we use these this sort of spectral order, what we can do is we can make sense of it so that we can find color combinations that work for us in art and design. And obviously, you know the primary colors: red, yellow, blue, 3 colors. When we use a color palette, and this is for paint primarily, or paint or pigment or any actual physical material, right? Printing is a physical material. It's essentially a kind of paint. Our secondary colors, orange, green, and violet, which you all know, and then our tertiary colors are the primary color mixed with a secondary color, which gets that tertiary color. Tertiary means third, right? So blue, green, blue, violet, red, orange, yellow, green, right? We split colors up into an order that gives us both a warm moniker and a cool moniker. So warm colors, if I say, oh, you need to make that warmer, I would really, really try to really push that towards the warm end of the spectrum. I would say those are colors that exist on, like if you, the colors that you would see in a fire, except for that little bright blue light that's right in the center. Okay, so any color that you would see in a fire can be constituted as a warm light. And then obviously the cool colors are colors that you typically see possibly in a landscape. I want you to note though, that in between yellow and green, so yellow being our warm and green being our cool, we've got yellow-green, which can kind of err on either side. So there is an in between, right? A hue is just simply a fancy name for color, okay? And that hue has an actual color in the color wheel that's been named. You don't make them up. Each color has a value, which basically means how dark or light it is. So instead of saying we shade things, we refer to its value. And that doesn't mean how much money it's worth, right? We're talking about its relative lightness or darkness. When we add white to a color, we're calling it a tint, even on a screen. And when we add a shade to a color, we're mixing it with black. Okay, and black is used in CMYK. K is what black stands for. So black is actually used in order to create a color. Believe it or not, if you're a painter and you're using the subtractive method, which uses paint, if you take yellow and you add black to it, you actually create perceptively a green. So you'd be surprised the more you, and that's why we ask students to take things like painting classes, because you'll understand a lot more about the printing process in general if you became a graphic designer. Color harmonies are basically colors that for the most part theoretically are supposed to work really well together. And the more you understand about color harmonies, the more of a master you're going to become at it. So complementary colors are obviously colors that are directly opposing each other on the color wheel. So blue-green's opposite is red-orange, right? Monochromatic color harmonies typically work really well together because they only are one color of the same body, right? So a monochromatic color scheme could be yellow and yellow-orange, right? Or all versions of yellow. When we use an actual pigment, so either in the printing process or something like paint or even like silkscreen, we're referring to that as a subtractive process, which is why I've got the difference between the gels there and then the paint on the bottom. So the illustration there is an opposing process, which weirdly, if you mix the complements according to, or sorry, not the complements, the primaries according to color theory in the subtractive process, which uses paint or pigment, you add yellow, red, and blue. What's happening is that it actually makes a black or something really close to a black if you've got really high quality pigments. Now, interestingly enough, the opposite happens when you use light. So when you shine all of those gels on the same spot, it gets a white, which is why we refer to it as a different process. So here's an illustration simply of RGB versus CMYK. It's very simple. It's just simply a way to organize the understanding of that color. And the subtractive process is which one in this illustration?
The CMYK, the print.
Yeah. Because all of those colors together, even though it's not like a true color wheel in the way that we're used to it, that magenta is to act as our red. When they interact together, we create essentially a black, a rich black. And printmaking really does that well for us. So when those colors are used in conjunction with one another, those tiny little dots basically create a form of theory, of color theory, called optical mixing. And if you grew up with an actual television set, that's how we saw color in television. It's tiny little dots that that are using light as a means to interact and to overlay in order to create these mixtures in our mind, where we perceive an orange when magenta and yellow are mixed one over the other. So an illustration of value in color. So we've got the tints of the Pat Steer in the middle, and then we've got the shades of the Pat Steer paintings at the bottom. And then we've got a value scale, which is right here. Excuse me. Usually humans can see like 25 to 30 values in life around them. The reality is we oftentimes can't render that many values, even though our computer can, which is oftentimes why you see such a vibrancy in illustrations that are created on the computer in a way that paint maybe has a limitation to. And even print kind of has a limitation to. So, all right, it gets a little bit more complicated. The illustration on A is just simply the spectral colors and their corresponding values. So if I take a Xerox copy of my 12 color wheel, that's what it looks like. So each of those colors has a value. Yellow is obviously the lightest, and purple is obviously the darkest. Blue is a range of values by adding white. That's one way to add a value, okay? C is yellow-orange with gray mixed in, just black and white. So that's called an achromatic gray. Black and white mixed together with a color will create a neutral color that is also darker, okay? D gets a little bit more complex. So if we start with the exact same color, or yellow-orange, and we're adding the complement to it, what we're getting is a more varied, darker version of that color that is actually called a chromatic gray. So achromatic means without color, and chromatic means with color. The intensity and saturation will always be a function of the brightness or darkness of a color. And we can brighten or darken a color in two ways, illustrated here, by adding its complement or by adding black and white, okay? So those are the two ways to really dull a color. So basic color theory tells us that color evokes a psychological and physiological response. In the West, we associate black with mourning, okay, and death. In the East, they associate white with mourning and death. So when I talk about a psychological and a physiological response, when you see a color, that oftentimes has an environmental effect. You may have a sociological response to something because of the culture that you've been raised in. But the reality is any physiological response will tell us that if you paint a room red, the best room to do that in is probably your dining room, because red oftentimes makes people hungry, right? So physiological, your body actually has a response to it. So color is a function of light, and without light, there can be no color, right? Because the whole spectrum is essentially white light, okay? And those are really important ideas to sort of get a grasp on. Yes, certain people do see different colors, but that's color blindness, right? That has to do with the frequency and the cones and rods being displaced, and not being able to read certain spectral colors in the same way that everybody else does. But relatively, most of us see color in the exact same way. And we can measure color using a spectrophotometer. And that's a scientific device that will actually say, this is a true yellow or this is a true blue. So all colors are dependent on light. When light strikes something, now here's a concept to wrap your head around. When light strikes something that is red, all of the colors except for red are actually absorbed. So to say that that is a red ball, what's actually the scientific truth of that is that that ball is not red at all. That ball is every single color except for the red that you see, because it has to do with light, because without light, we don't have color. So wrap your head around that. This is a test to be able to see if you are colorblind. Males typically are more often colorblind than those born female. That has to do with just sort of a genetic order of things, just the way it goes. I have no idea why. This is the test invented by Japanese scientists to be able to see if you can see. So what are we looking at? We should be seeing two numbers here. What are they?
3 and an 8.
A 3 and an 8. If you don't see that 3, that may mean that you might be slightly colorblind. You can't, it is a range. If you don't see an 8, you might be blind to oranges. If you see nothing, you might be completely colorblind. So it all has to do with this sort of ratio of what we are able to perceive. Oh, and if you,
oh,
yeah, go ahead.
I have a question about the colorblind test. Would you know why they use like dots? Like,
Yeah, if you squint your eyes at this right now, really, really squint them, you shouldn't see a number.
right.
And so what this premise works on is that you're only seeing the value of those colors rather than the colors themselves. But if you open your eyes, you're able to see these colors and separate each thing from the next because of Gestalt, right? And we talked about Gestalt a little bit during composition, when I talked about composition. You're able to take in the parts of the whole if you open your eyes bright and wide. But if you squint your eyes, you're only able to see basically the circle. And you know that it's kind of dots, but you don't know really when colors end and colors begin. Does that make sense? So if you were to take if you were to take a Xerox copy of this very test, just as black and white Xerox copy, no color, they would just look like dots and they'd all be the exact same value, for the most part, the same value. But because this red is exactly the same value as this green, that's what's happening. So it works on value. Does that kind of answer your question? Kind of?
Yes, it does.
Okay, great. All right. There's going to be a saying that you come across in art school all the time. Warm pops, cool recedes. What does that mean? It's based on the understanding of atmospheric perspective, the way the world actually works. When warm things are put, like reds, oranges, when warm things are put in a composition, they tend to move forward in space. We read them as closer to us than when cool things get put into a composition. And we can really, really see this in the landscape to the right, because that building that's closest to us, we kind of see some oranges in it a little bit. It feels yellower. The things that move farther away, with the exception of that one single little building there, get more purple, get more bluer, get kind of hazy, right? So warm pops, cool recedes. Even if this were just an abstract composition, the warm things would look like they were closer to us and the cool things would look like they were further away. So know that in order to use it. All right. We know the color wheel here. We don't know I have that. When you use two complementary colors that are a very, very similar value, like this illustration, same value, not really complements, but they're different temperatures. When you use actual complements, oftentimes, if we use them in the same value, so if we were to take a Xerox copy of them and they'd be essentially the same value, what happens is vibration. The eye moves them back and forth and we see movement. This isn't true. This isn't an absolute true illustration of that, but this is a painter who actually is illustrating this notion of agitating the eye using complements and complements of a very similar value. You see these gears appearing to move because it's not necessarily complements. They're really close. We've got this sort of semi-purple, blue, and then this kind of icky yellow, right? Because they are opposing on the color wheel, they appear to move and vibrate against each other. Know this to use it, because it's not generally very pleasurable to look at. See what I mean? Mm-hmm. Optical mixing, I illustrated it before, is when the viewer's mind mixes the color in your brain. And this is an artist named Chuck Close, and his work exclusively touches on this. He's a painter, and this is a close-up of one of his paintings, right? And so he's using this dot abstraction within each little square of the grid that he's superimposed over his painting. And the eye and the mind optically mix in order to create a visual whole that makes sense, right? We understand that his suit is a kind of gray blue, but the reality is if we look close up, we're going to see all kinds of colors if we break it down. So there are some formulas for color harmonies, and that means harmonies, they work well together. So the first one we want to talk about are analogous. Basically, that's three colors on the color wheel that are right next to each other. So this little plant illustration here is a color harmony that aesthetically appeals to most people. It's a matter of taste if you don't like it. Monochromatic colors are colors that exist just in one place on the color wheel, just one, but they might have different values. I want you to see how all the greens in this interior have different darknesses and lightnesses to them. But for the most part, they're all green. Then we have what's called a triadic color scheme. And that's a color scheme where you pick one color, you shoot to the middle, and it's the colors on a direct 45 away from that color. So you're not using the complement, you're using the colors that are directly spaced out in order to create a perfectly symmetrical triangle. That's called an isosceles triangle, right? Right? Yeah. It's been a while. But either way, they're the colors that are completely equally spaced. And I can spin this in order to find that color combination. I personally, as a matter of taste, don't like a triadic color scheme, but color theory tells us that most of us do. So that's why I meant what I meant when I said matter of taste. Then we have what's called a tetradic color scheme. That's when you are picking 4 colors and you're picking the complement. So I picked this color here, and it's the color directly across. And then I arbitrarily pick this color over here. It's just arbitrary. I just chose it because I like it. And then it's the direct color across. And only using those colors in order to create a color combination that is supposedly aesthetically appealing. Then we have split complementary colors. So I pick, say, this yellow-orange. I look directly across the color wheel, but I pick the 2 colors that are right next to that color. Okay, so I'm splitting the complements. Instead of using that complement, I'm using the color next to it and the other color next to it. And then we have complementary color. Yeah, go ahead. Question.
And what is that called?
Split complements.
Right.
Okay. Then we have just the simple one, which is any complementary combination. So what we've got here is that sort of yellow-green, right? And instead of it being the perfect purple, it's sort of a red purple, right? And we'll see that in this photograph here, at least as an illustration. This is oftentimes colors that you'll see in a natural environment, especially with florals. Okay, in review, warm colors. Those are colors that evoke warmth because they look like sun or fire. Cool colors, colors that oftentimes you see in a landscape, like in water or grass or ice. Neutral colors. Those are grays and browns, okay? We don't really see those on the color wheel because neutral colors only occur when we're mixing colors. Got it? Then we have the value, and that's the lightness or darkness of a color. But the brightness of a color refers to the amount of white, okay? So the more white that's in a color, we're going to say it's brighter versus saturation. Don't confuse brightness and saturation, y'all. Okay. Saturation is when a color is at its most pure and it's not mixed with anything other than what's on the color wheel. Does that make sense to everybody? Yes, Melissa, I totally understand. No, Melissa, I have a question. You with me?
Yes.
Okay, great. I want to hear from somebody else other than Pam. Pam, I know you're with me. I feel your presence. All right. Then we have a color scheme that's simply based in nature. This is also called a color inventory. At the end of the term, we will probably do an assignment using color inventory, because if you feel like you've got a bad color sense, I feel like I actually have a bad color sense. Basically, it's the practice of finding a source image and going, I like the colors in this source image, and only using the colors in that source image. You know that it's going to appeal to you. You know that it's going to be harmonious because you found it in an image. And it's a very easy technical way to find something that you know is reliable. So here's an illustration of value and color. We can add value to a color by either adding black, like this one, or by adding white in reverse, or the complement. The intensity of a color, so we have 2 complementary colors here, this blue and this orange. The intensity, when we mix, so what's happening here is this blue is getting mixed with a little bit of this orange, and that's what's getting here. If we take the exact same ratio of the same amount of this blue and this orange, and we mix them together, we get what's called a neutral gray. Memorize that. when you use two complements in exact ratio to each other, they basically cancel each other out into a neutral gray. If we use a little bit of the complement when we mix a color, like here, we get a darker and a duller color. Is everybody clear on that? I want you to walk out of this lecture understanding that concept. And I want to hear someone beyond Pam. Does everybody understand that concept?
Yes.
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 Fabulous. So what happens when you mix a complement in equal ratio? What happens? What's it create?
Neutral.
Neutral gray. What happens when you just mix a little bit of the complement in something? No, Pam. What happens?
It's a tint
No.
or it changes the intensity.
Yes, it dulls it. Dulls.
Okay.
Okay, great. So as long as you guys understand that. All right. Color theory has had a lot of science behind it. And a lot of people have really progressed with the way we see and understand value. When I have a student print out a work of art, whether they're mounting it, matting it, whether they're printing it on a piece of paper, I never have them mounted on black. Why? Because when you take a color, a saturated color, and you put it on a field of black, it dulls the color perceptually. Our eye and mind perceptually take that color away. The color does look brighter in value, but it doesn't look pure. Okay? So things will happen to an edge, and I'll show you a few more. When we take the same color, this is exactly the same color, and we put something of a similar both tone, so it's the same kind of cool tone, and a similar value, it doesn't appear as hard-edged. I want you to look at those edges here. It doesn't appear as hard-edged as the image on the right, with the green on the orange. So because these are two different temperatures, contrast is increased. When we take a completely neutral gray, black and white, there's no color in these grays, none. They appear to be colored when we put them on a field of color. Do you see how these grays look warmer and cooler based on the context we put them in? This is called the concept of color interaction. There's a wonderful book that I think that all art students need to at least flip through, if not own, called The Interaction of Color by Johann Itten, I-T-T-E-N. And these are all directly from that book. Okay, so he's the one that discovered all of this and was able to verbalize it and give us a sort of reliable science in the art world. So red, purple squares, all the exact same. And look at how differently they appear. And granted, this isn't as bright as I would like it to be. You can actually type in Johann Itten elements of color, and you can go to the website and actually see this on a much better resolution. Okay. All right. There are all kinds of color modes in Photoshop. And I'll kind of mess around with those on Monday with you in person. I'll give a demo. And this is basically like, oh, I want to put my little niece into this photo of a landscape, but they just don't work in the same color, right? So there are different color modes that you can actually play with in Photoshop to make them believably situate themselves in the same space. And here's a few of them. Dissolve, multiply, screen, you can dodge, and we'll talk about those at length on Monday. We can also use a concept, and it's a relatively new concept in Photoshop, where it automatically color grades for us. So we can take one image and we can situate the figure or the photograph itself into very different color scenarios, right? And we used to have to paint all of this. So now it's an automated AI setting, and life is different for anybody wanting to do some digital painting now. So here's an example of that. And I'm going to teach you how to do this, like I said, with just a few short maneuvers on Monday. So we have the original image here, and then we have the color corrected, color graded image. So all those little filters that you see on like Instagram, that's actually taken from Photoshop. And reminding you, everything that you can do in Photoshop originally, and still today, you can do in a darkroom. So we'll talk a little bit about that at length. I won't go through this because it's getting a little bit more. But we can use blending modes in Photoshop in a variety of different ways. And it's over in the layers panel. So if you want to play with it over the weekend, you can. But there are all kinds of blending modes. These are all of them, right? We can use a soft light. We can use a linear burn. We can play with the saturation. So we can really, really manipulate photographs using this concept called color grading, okay? All right, here's what dissolve looks like. Here's what multiply or dissolve blending mode looks like. Here's more for that. And these are going to look like subtle shifts, but they really do increase the sort of believability of a photograph, especially if what you're doing is digital illustration. We can also make a photograph that's shot in the day look like it's shot at night using screen blending mode. And then we can use color dodging, which basically is like pushing other areas of color either back or forward, kind of like a vignette, but selectively not at the edges. And then we can overlay color. So if we want everything to kind of look like it has a blue cast or a yellow cast, we can use a digital overlay. We can have hard light, so really directional light, as if it looks like light, you know, like at 10 o'clock in the morning coming up from the ocean. All right. I am going to stop share.